today's lecture, I am going to talk about rotational spectroscopy. First, we will look at principle behind rotational spectroscopy, and then we will go forward and see what are the applications of rotational spectroscopy. We will also look at rotational Raman spectroscopy and see what are the different aspects of rotational Raman spectroscopy. Rotational spectroscopy, as the name suggests, it involves the transition between quantized rotational levels. Generally, the gap between two rotational levels is of the order of 10 to 1000 joule per mole. When a molecule absorbs microwave radiation, it undergoes rotation. So, rotational energy levels are quantized. It means that not all the value of energy is allowed, only certain value of energy is allowed. The way we solve the wave function and energy of quantized energy levels is by using a wave equation known as Schrödinger wave equation. So, here what we do is we apply your Hamiltonian operator on the wave function to get, this is Hamiltonian operator on the wave function to get energy as the eigen value of that operator. Your Hamiltonian operator consists of two different operators. One is your kinetic energy operator, and that is given by minus h square by 8 pi a square m d2 by dx square, and then you have a potential energy operator which is given by V. So, your Hamiltonian operator is basically sum of kinetic energy operator and potential energy operator, and when it is applied to a wave function, you can get the energy of a particular energy level. So, solution of this equation gives both the wave function associated with the energy level and the energy associated with the different levels. So, we can calculate energy of rotational level by considering the rotation of a rigid rotor. So, this is your rotation, and this we are assuming a molecule as a rigid rotor, and now we are going to solve your Schrödinger equation corresponding to rotational motion to get the energy of rotational levels. So, first we will try to simplify it. We will just look at rotation in two dimensions. So, let us consider about rotation of an atom about a fixed point. So, here is an atom with mass m, it is rotating with a frequency nu around point O. If distance between O and this atom is r, we can calculate velocity by using this formula. So, velocity will be equal to 2 pi r into frequency. This can also be given in terms of angular velocity, v will be equal to r omega. Once we know v, we can calculate kinetic energy, because kinetic energy is equal to half mv square. So, if we put value of v from here to this equation, then we will get kinetic energy which will be equal to half mr square omega square. Mr square is known as moment of inertia and given by symbol I, and so kinetic energy can be written in terms of I and omega as half I omega square. Similarly, we can write equations for angular momentum. Angular momentum will be equal to I omega, and if I put value of I from here and omega from this, we can get L is equal to mvr, and since mv is equal to momentum, so your L is equal to p into r. Kinetic energy can also be expressed in terms of angular momentum, we know that kinetic energy is half I omega square. So, this will be equal to L square by 2 I. So, L, we know that L is I omega. So, if you do a square of this divided by 2 I, what you are going to get is half I omega square. So, this is about kinetic energy and angular momentum of an atom rotating about a fixed point. Now, let us consider rotation of diatomic molecule around center of mass. So, diatomic molecule has two atoms with mass m1 and m2. Suppose it is here is center of mass and the molecule is rotating around center of mass. Molecule is rotating around center of mass. If it is rotating around center of mass, it must follow this equation R1 into M1 is equal to R2 into M2, where R1 is distance of atom 1 to the center of mass, where R2 is distance between center of mass and atom 2, and the distance between atom 1 and atom 2 is given by capital R. So, capital R is basically R1 plus R2, and if I put R2 value from here to this equation, what I will get is R1 M1 by M2, and now I can take R1 out and I will get 1 plus M1 divided by M2, and this is basically R1 multiplied by M1 plus M2 divided by M2. So, this R, capital R, can be written in terms of this distance R1, which is basically your distance between center of mass and atom 1. So, this R1 can also be expressed in terms of this capital R, and it will be given by R1 is equal to M2 divided by M1 plus M2 into capital R. Capital R. You can see here that R is equal to R1 multiplied by M1 plus M2 divided by M2. So, if I want to calculate R1, I will take this to left hand side, and when we do that, M2 will come in the numerator and M1 plus M2 will come in denominator. So, R1 is equal to M2 divided by M1 plus M2 multiplied by R. Similarly, we can calculate R2. R2 is M1 divided by M1, this is M1 plus M2 multiplied by R. So, now we have expressed R1 and R2 in terms of capital R, which is the distance between two atoms. Distance between two atoms. Now, we can go ahead and calculate kinetic energy. Kinetic energy will be given by half M1 R1 square omega square plus half M2 R2 square omega square. If we take omega square outside, what we will get is half M1 R1 square plus half. So, this half you can take out, then you are left with half M1 R1 square plus M2 R2 square into omega square, and this is equal to your I. Here you see I is equal to M1 R1 square plus M2 R2 square. So, we can write kinetic energy equal to half I omega square, where I is equal to M1 M2 divided by M1 plus M2 into R square. So, if you go back, you see I is equal to this M1 R1 square plus M2 R2 square, and if you put the value of R1 from here and value of R2 from here, what you are going to get is I is equal to this equation M1 M2 divided by M1 plus M2 multiplied by R square. This whole thing is called reduced mass and given by symbol mu. So, I is equal to mu into R square. I is equal to mu into R square, and so mu is equal to M1 M2 divided by M1 plus M2, M1 plus M2. If you inverse it, 1 by mu will be equal to your 1 by M1 plus 1 by M2, and so that your this inverse is equal to m 1 plus m 2 divided by m 1 into m 2, m 1 into m 2. And we know that kinetic energy, this is your kinetic energy is L square by 2 I. So, if I put I is equal to mu r square, we can get L square by 2 mu r square. So, kinetic energy of a diatomic molecule rotating about center of mass is given by angular momentum square divided by 2 pi r square. And then we can simply get Hamiltonian from this angular momentum, and Hamiltonian will be given by only kinetic energy operator, because in this case potential energy is 0, and so your Hamiltonian operator will be equal to kinetic energy operator, and that will be given by L square operator by 2 mu r square, and that is equal to h cross square minus h cross square by 2 mu multiplied by del square. So, Hamiltonian of a rigid rotor is given by your this equation h psi is equal to minus h cross square by 2 mu del square psi. This is your Laplacian operator, and that will give you your E psi. Here del square is equal to d square by dx square plus d square by dy square. So, del square basically Laplacian operator is equal to d square by dx square plus d square by dy square. This is, we are talking about rotation in a plane, rotation in a two-dimensional plane. But to solve this equation, this Schrödinger equation, we need to convert this equation from a Cartesian coordinate system to your Cartesian coordinate system to polar coordinate system. Once we do that, then we will be able to solve the Schrödinger equation, and we can get energy of different rotational levels. So, using x is equal to r cos phi and y is equal to r sin phi, we can convert this Laplacian operator in the terms of differential with respect to r and differential with respect to phi. So, this is your Laplacian operator, and now we are going to use it to calculate kinetic energy part and overall energy. So, overall energy, the operator Hamiltonian operator will be given by just kinetic energy part, since potential energy is 0, and then you have this operator in the polar coordinates. Now, this operator again, since we are assuming the rigid rotor, so r part is constant. What does that mean is this differential part is going to be 0. So, your Hamiltonian is a simplified term which can be expressed in terms of a differential with respect to phi. So, this is your Hamiltonian operator. Now, if we apply to the wave function of this rotational motion, then we can get energy. So, you have minus h bar square by 2 I d square by d phi square, and if you bring it here, minus E psi phi is equal to 0, and just to simplify it, just multiply this equation by your minus 2 I by h bar square, you will get this equation. Why we are simplifying this? Because solution of this kind of equation is well known. We can express this equation into another simplified equation, where you can assume that 2 I by h bar square E is equal to m square. That is what we do, assumption. And if you do that, now solution of this equation is well known. And here we have assumed that 2 I by h bar square into E is equal to m square, and that can be used to calculate the energy of your two-dimensional rigid rotor. So, this is the equation, the differential equation, which is a function of phi, and solution, this is well known, and the solution is simply exponential I m phi, exponential I m phi. And exponential I m phi, if you take a differential of this, what you will get is I m exponential I m phi, and double differential will give you I m square E I m phi, which is nothing but minus m square the multiplied by wave function. So, you see that this differential will be equal to minus m square by into the wave function. And so, it is quite simple differential equation, and that is why we did so many simplification. So, once you know the solution, now we have to apply boundary conditions, because wave function must match as rotor starts another rotation after completing the wave function. So, this is boundary condition. So, allowed values are when m is equal to integer, because once you have like that, your psi at theta will be equal to psi 2 pi plus theta. And that is only possible when m has integer value. If m is not an integer, then you can see that psi is not matching after one rotation. Psi is not matching after one rotation, and thus m can take only some specified value, and since energy is dependent on m, your energy has some specified value, and that is why you say that energy of a rotational levels are quantized. So, E is equal to m square h bar square by 2 I, that is what we assumed last time, and it is dependent on quantum number, and m can take value from an integer value. We know that energy is your Lz square by 2 I, and from that we can get Lz value, which is m h bar. So, for two-dimensional rigid rotor, we have one quantum number, that is m. Your linear momentum is given by this, and for different value of m, you have energy. So, for example, if you take 6, then this is 6 square h bar square by 2 I. So, 36 divided by 2 is 18 h bar square by I. So, this is 18 h bar square by I. Similarly, for 5 it will be 12.5 h bar square by I, and for 4 it will be 8 h bar square by I, and Lz value is simply m h bar. So, 6 h bar, 5 h bar, 4 h bar, 3 h bar, and just like that. So, here we need only one quantum number, which is m, to define the energy. And so, now let us go to three-dimensional rigid rotor. So, for the rotation of three-dimensional body, we will take, this is your coordinate system x, y, z. So, now we are not only just looking at the rotation in x, y plane, but we are looking at the three-dimensional plane. So, let us assume that this angle is theta, this is your rigid rotor, and this makes angle theta, here is your atom, and this makes r, this distance is r, and so this is the angle, theta is the angle with the z axis. If you take projection of this on xy plane, then phi is the angle between x and this projection. Angle between projection and x axis is phi. Now, you can think of, here is r and this angle is theta. So, this is your r cos theta. So, z value is your r cos theta, and then if this is r cos theta, this will be r sin theta. It means this is also r sin theta, this is r sin theta, and since this angle is phi, so x is equal to r sin theta cos phi, and this will be y is equal to r sin theta sin phi. So, using that, now we have seen that what is the relation between r theta phi with x y z. So, now we can go and calculate or see what will be the Laplacian operator in polar coordinate system. For that we need to calculate volume element, and now you see the way we do is, so this is if you remember, this is theta and this is your r. So, this will be r cos theta and then this will be r sin theta. So, this is your r sin theta, and if this angle is phi, then this angle is phi. So, whole length will be r sin theta d phi. This angle is your d theta. So, this length will be r d theta, and since this is dr. So, now you have a volume element is equal to r square sin theta d phi into dr. So, you have your this is r sin theta d phi multiplied by your r dr and multiplied by your. So, this is this, and this is your r sin theta and r d theta. So, you can calculate the volume element. Once you know that, then you can express your Laplacian operator in a spherical polar coordinate, and this is the way you can express Laplacian operator in spherical polar coordinates. Now, since we are again taking rigid rotors, what does that mean? That this term will go to 0 because your r is constant. So, your Laplacian operator will have only dependence on theta and phi, and since your wave function depend on theta and phi, if we are assuming that your this rotation is like a rigid rotor, and that kind of wave function is known as spherical harmonics. So, now we are going to apply a Hamiltonian operator on this spherical harmonics to get your energy, and this is the again we applied Hamiltonian operator, or we can say Laplacian operator in polar coordinates on the spherical harmonics, and what we expect to get is energy of the rotational levels. Okay, so, again we will try to simplify and express this whole differential equation in form of a standard differential equation, so that we will be able to solve it. So, first thing what we did is just multiplied by sin square theta 2 I by h bar square, and what we will get is this term, all this term. Okay. And here we assume beta is equal to 2 I e by h bar square. So, here beta is 2 I e by h bar square. So, simple thing is we are trying to express this in a well known differential equation whose solution is known. Okay. So, sin theta del by del theta sin theta. So, dy by d theta del 2 y by del phi square beta sin square theta y theta phi is equal to 0. One of advantage of this is that now you can see that you are able to separate your theta part with phi part. So, this is only function of theta, this is only function of theta, whereas this is function of phi. So, this is whole purpose of this multiplication. Now, if we have this kind of differential equation, then you can divide your wave function into two parts, one which is function of theta and another which is function of phi. So, now what we are doing is we are expressing your spherical harmonics into a function which depends only on theta and a function which depends only on phi. When we put that, what we are going to get is, so this is totally function of theta and this is totally function of theta and this is function of phi. So, when you substitute that, that is what you are going to get, and since the two parts are either dependent on theta or phi. So, the two terms must be equal to some constant, and here we define this is equal to m square and if this will be m a square. So, this will be minus m a square, and so whole term will be 0. So, this plus m a square minus m a square, that will give you 0, and now it is easier to solve these two equations. This we have already solved when you are dealing with 2 dimensional rigid rotor, and solution this is well known, and that will be given by exponential I m phi multiplied by a normalization factor. Again m can take value from 0 plus minus 1 plus minus 2. Now, the second differential equation, we will look at how to solve this. So, this is your sin theta by capital theta, which is a function of theta. So, capital theta is basically for wave function, where theta is for the angle, a small theta is for angle. So, sin theta by capital theta, del by del theta sin theta, again this is the differential, and this we need to solve if we want a solution. So, one thing we can do is just divide by sin square theta, and when you do that, what you will get is here sin theta at the denominator, and then this will cancel out, and minus m a square, if you take left hand side, you will get minus m a square by sin square theta. Again, these all things are done to simplify the equation. So, in the last slide, we obtained this differential equation. Now, what we are going to do is simplify a bit to make it into some standard differential equation which solution is known. So, first thing what we do is multiply this equation by the wave function cap theta, cap theta. If we do that, this cap theta will get removed and will get multiplied by this factor. So, you see theta theta multiplied by this factor. And now, what we will do is we assume z is equal to cos theta. Z is equal to cos theta. If z is equal to cos theta, then sin square theta will be equal to 1 minus z square. So, first thing is sin square theta is 1 minus z square. Now, if we differentiate this, z is equal to cos theta, what we are going to get is dz is equal to minus sin theta d theta. What does that mean is del by del z or d by dz is simply d by minus sin theta d theta. And once we assume this, now we are going to simplify the second equation. So, 1 by sin theta del by del theta, if you see here, 1 by sin theta del by del theta is equal to minus del by del z, and that is what we substituted here. So, 1 by sin theta del by del theta is substituted by minus del by del z. Similar thing we are going to do here, and the way we can do is, let us take this sin square theta by sin theta. So, what I did is I multiplied sin theta in the numerator and divided by sin theta in the denominator. Why I am doing that? Because I know that 1 by sin theta del by del theta is equal to minus del by del z. So, del by sin theta d theta is equal to minus del by del z. So, you can do minus here plus. Okay. So, if I do that, then 1 by sin theta del by del theta is equal to minus del by del z, and sin square theta remains. Sin square theta remains, and then you have plus part, same thing we can take from the second line. So, beta minus m a square by sin square theta, and then cap theta, which is function of theta, is equal to 0. Now, you see sin square theta we just expressed in terms of z, and sin square theta is 1 minus z square, just put it here. So, you will get your sin square theta is 1 minus z square, and this minus minus becomes plus. Similarly, we can replace this sin square theta by 1 minus z square. This is well known differential equation. This is a well known differential equation which is known as Legendre differential equation. Legendre differential equation, which solution is known, And so, this is your whole equation, that is what we got, del by del z 1 minus z square dpz by dz plus beta minus m square 1 minus z square pz is equal to 0. Here z is equal to cos theta. So, just by putting z is equal to cos theta, you are able to get a differential equation which is known by name of Legendre differential equation, and the solution of this is well known, and that is why we were doing so many simplification. So, in this case you will get a multiple value of your wave function and energy, and the way to solve it, give beta is equal to j plus 1. So, beta is equal to j plus 1. For each value of j, there will be a different solution, and we will go and show how solution is value of j and m, you can get different solution, and those are the allowed wave function for the rotational level, and the corresponding energy is the energy of that level. So, let us think about differential equation for m is equal to 0 and j is equal to 0, and what will be its solution. So, this was the differential equation which we just seen in the last page. So, if we put m is equal to 0 and j is equal to 0, what you will get is this equation. So, this part is 0, this part is 0, and so you are left with just the first part, del by del z 1 minus z square del p z by del z is equal to 0. So, now think of solution of this differential equation must be a constant, because if you take constant, then this will be 0 and the whole thing becomes 0, and then differential will be 0. If suppose you take some function of z, then you see that z square will get multiplied by some constant if it is first order. If it is second order, it will be multiplied by z, and the differential of that is not going to be 0. So, only solution of this differential equation is constant, and so a into 1, and if you put 1 here, you can see that if you put 1 here, then this will be 0 and everything will be 0. So, solution of this equation is z is equal to 1 or z is equal to a constant. Now, let us think about if we try to solve this differential equation for m is equal to 0 and j is equal to 1. So, if we put that m is equal to 0, then this part is going to be 0 and this part is going to be equal to 2. So, j is equal to 1, 1 plus 1, 2, 1 into 2 is 2. Now, the solution of this differential equation will be different than the first differential equation. So, this can be solved if you take p z is equal to z or p z is equal to z into some constant. So, if we do that, let us see here, if we replace p z by z, then we will get del z by del z cancels out. So, 1 minus z square, and differential of that is 2 z. This will be, I think, minus 2 z. So, this is minus 2 p z, and minus 2 p z plus 2 p z will be 0. Minus 2 p z and plus 2 p z is equal to 0. The solution for the differential equation which we got for m is equal to 0 and j is equal to 1 will be z multiplied by some constant. Now, similarly, you can get differential equation for m is equal to 0 and j is equal to 0. If you put here, this is again 0 and 2 into 2 plus 1 is equal to 6. So, this is differential equation, this is different from the earlier two, and solution is certainly going to be different, and the solution is 3 z square minus 1. If you just differentiate this, you will get 6 z, and if you double differentiate, what you are going to get is 6 minus 18 z square, which is equal to minus 6 p z, minus 6 p z, and if you add here, then it is going to be 0. So, we have seen the solution of 3 different differential equation for different value of m and j, and what we have got is different solution for each for each m is equal to m and j value. So, what these 3 solutions tells us that we can get wave function, your theta will be pz, and this z will depend on your j and m quantum number, and this is known as associated Legendre polynomial, which will be different for different value of j and m. The solution what we got is, if j is equal to 0, m is equal to 0, we will get 1. If j is equal to 1 and m is equal to 0, then you will get z. If 2 0, then you will get half 3z square minus 1, and similarly for different value of j and m, solution will be different. Here again I will emphasize that z is equal to cos theta, z is equal to cos theta. This all solution can be written in a simple form which is given by the associated Legendre polynomial. Your L is basically j. So, Pjm is a function of cos theta, which we are writing z, and that will be given by sin m theta differential of d cos theta power m and Pl cos theta, where Pl cos theta is given by this. If m is equal to 0, this turns out to be 1, and you have simply Pl cos theta, which is given by this equation. So, all the polynomial solution can be expressed in terms of this differential, So, now we know the solution of theta part and solution of phi part. Now, we can go and see what will be the spherical harmonics. So, let us first see if we take j is equal to 0 and m is equal to 0, what will be the wave function for theta part. So, what is the solution for the theta part? So, this is given by cos theta and 1 by 2 0. If you remember that if m is equal to 0, then we are left with only Pj cos theta or Pl cos theta, and that is given by here. So, now we are going to put the value of j, which is basically L. So, L is equal to 0, m is equal to 0, here L is equal to 0 and then L is equal to 0 here. So, if you put that, what we are going to get is 1, and if you remember that the solution which we got for the j is equal to 0, m is equal to 0 is equal to 1. So, here you have 1, and now we know the solution of phi part also, and that is 1 by root 2 pi e exponential minus m phi. So, m is equal to 0, and so you have simply 1 by root 2 pi, and so your spherical harmonics will be your 1 by root 4 pi. The spherical harmonics will be 1 by root 4 pi, and since spherical harmonics for y 0 0 is constant, so S square is also going to be constant, and that tells you about distance of surface from the origin. So, for any value of theta and phi, y is going to be constant, and so it will have a constant value, and so a shape will be like a sphere. Now, for L is equal to m and m is equal to 0, again if you solve this, you will get the term cos theta, and so a spherical harmonics is root 3 by 2 root pi cos theta. Now, you see it is dependent on theta, it is not dependent on phi, but it is dependent on theta. So, let us see how does it will look like. If we have L is equal to 1, m is equal to 0. So, the square of this spherical harmonics will be a function of cos square theta, and this will give you a distance of surface from origin. Now, let us take the value of theta from 0 to 90 degree. What you will see? At 0 value, you can see you have got the maximum value of cos square theta. What does that mean is, when theta is equal to 0, this your distance of surface from the origin will be maximum, and you can see this is your theta is equal to 0, this is your theta is equal to 0, and so you have a maximum value. Now, you change angle. So, suppose you are going to 30 degree, this value is decreasing, 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 and at theta is equal to 90 degree it becomes 0. So, you can see here it is 0, and since it goes to cos square theta. So, same thing will happen when you go in opposite direction. So, this gives you shape of PZ orbital. Similarly, for L is equal to 2 and M is equal to 0, your spherical harmonics will be dependent on 3 cos square theta minus 1. It will dependent on 3 cos square theta minus 1, and I have calculated the value of cos square theta for given value of theta, and then we calculated 3 cos square theta minus 1. So, we are going from 0 to 5 by 4, 1 by 2, 1 by 4 to minus 1. So, now you see at 0 it is your maximum value. So, you are getting a maximum value at this point, and that starts to decrease. You see it becomes your 3 cos square theta 1 by 4, this kind of shape at the value of 0. If you change the value of m, then dependence of spherical harmonics or spherical harmonics will going to depend on phi also apart from theta, and in that case you will get a complex value. This so two values you will get, and these values are degenerate eigen function. Their linear combination is also going to be eigen function with the same eigen value, and so what is done is its linear function is taken, and now you can see that it is now dependent on sin theta and cos phi, sin theta and cos phi, and that gives shape of different p orbital px and py, and so this is your dependence of wave function or spherical harmonics and theta and phi. So, this is your overall spherical harmonics for value of j is equal to 0 and m is equal to 0, it is simply a constant. For j is equal to 1 and m is equal to 0, it is dependent on theta value. For 1 and 1, then it will depend on phi. 1 minus 1, it will depend on also on phi, and if again it is m is equal to 0, then it does not depend on value of phi. So, if m is equal to 0, the wave function is only dependent on theta value. If m is different than 0, then you have dependence of wave function of phi also. Okay, so, during the solving of this equation, we assumed we did two different assumptions. One is beta is equal to 2 I e by h bar square, and beta is equal to j plus 1, and this is going to give you value of E. So, since both are beta, you can simply write 2 I e by h bar square is equal to j plus 1, and that will help you in calculating value of E. So, this is the energy of your different rotational level, energy of different rotational level, and since j can take some integer value only, and so E is energy of rotational levels are quantized, energy of rotational levels are quantized. So, energy is given by h bar square by 2 I j plus 1. We can also calculate total angular momentum L square. L square is simply given by E into 2 I. So, E into 2 I h bar square j plus 1, or L is equal to square root of j plus 1 multiplied by h bar. We can also calculate the spacing between two different energy levels, and that is shown here, E j plus 1 E j. So, h bar square by 2 I will be common, and then j plus 1 j plus 2 minus j plus 1 will give you h bar square by I j plus 1. So, here we see that energy is only dependent on j, not on m, and so for different value of m. So, here degeneracy is there, and you will have 2 j plus 1 degenerate energy levels. So, let us think about how does this different parameters for 3-dimensional rigid rotors looks like. So, energy is your h bar square by 2 I j plus 1, your momentum is your h bar root j plus 1, and momentum along z direction is m h bar. So, for the 0, 2 j plus 1 is 1. So, its degeneracy will be 1, and your energy will be your, if you put j is equal to 0, then 0 into 0 plus 1. So, this will be 0. So, energy will be, so 0, energy will be 0, I believe. Okay. So, let us see here. If j is equal to 3, so 3 into 4, 12 divided by 2 is equal to 6 into h bar a square by I. This is energy for j is equal to 3. For j is equal to 2, you have a 2 into 3, 6 by 2 is 3 h bar a square by I. For j is equal to 1, you have 1 into 2. So, you have 2 cancels. So, 1 h bar a square by I. And for j is equal to 0, j is equal to 0, then this should be 0, this should be 0. Okay, you can calculate similarly L, and L will be this value. Now, you see this energy level, these are the different degenerate levels. So, for j is equal to 3, the 2 j plus 1. So, 7 levels are there which are degenerate, but their angular momentum will be along the z axis will be different. Along the z axis will be different. For 2, you have 2 j plus 1. So, you have 5 degenerate energy levels, 5 degenerate energy levels. So, this is about specifics of 3-dimensional rigid rotors. Now, in rotational spectroscopy, what we are looking at is the transition from one energy level to another. Since now we know what is the energy of particular level, we can know what is the energy difference between two rotational level, and once we know that, we can calculate what will be the wave number of frequency associated with that transition. So, E we already know is h bar square by 2 I j plus 1. So, we can calculate the difference between two energy level, consecutive energy level from j to j plus 1, and that comes out to be your 2 h c b j plus 1, 2 h c b j plus 1, where b is equal to your h bar square by 2 I h c, h bar square by 2 I h c. So, here it is in unit is in joule. So, we know that delta E is h nu, and that can be written as S c nu bar, where nu bar is wave number, and we already know what is delta E. So, now we can calculate what will be the wave number for the transition, and that is simply 2 b j plus 1. So, you must remember that you are going from the jth rotational level to j plus 1 level, jth rotational level to j plus 1 level, and so suppose you are going from j minus 1 level to j level, then your frequency of transition would be 2 b j. So, keep that thing in mind. Some of the books write frequency in terms of 2 b j, just 2 b j, where what they are assuming that your final energy level or excited energy level is j. So, basically they are looking at transition from j minus 1 level to j. Here we are looking at the transition from j level to j plus 1 level, and so your wave number is 2 b j plus 1, 2 b j plus 1. Now, we can also look at the difference between two lines in the spectrum. So, one line you are going to get at 2 b j plus 1. So, suppose if j is equal to 0, then you are going to get at 2 b, j is equal to 1, then you are going to get at 4 b and 6 b, like that. So, what is the difference between two lines? So, these are the different lines here of rotational spectroscopy, and what you are going to get is for 0 to 1 transition 2 b centimeter inverse, or in terms of hertz, it is going to be 2 cb, where c is velocity of light. So, 0 for one transition you will get, so 2b or 2 cb, 1 to 2 transition you are going to get 4 cb. This is the frequency, and the frequency, so spacing between the lines is going to be same. The spacing between lines is going to be same. So, this is your frequency for 0 to 1 transition, this is frequency for 1 to 2 transition, this is frequency for 2 to 3 transition, 0 to 1, 1 to 2, 2 to 3, 3 to 4. So, spacing between these two is going to be constant, it is going to be constant. So, it will be 2 cb hertz or 2b in centimeter inverse, 2b in centimeter inverse. Okay, so now we know what is the delta E, or your frequency and wave number associated with different transition. Now, we need to know the selection rule, which kind of transition are allowed, which kind of transitions are allowed. And for that we know that transition, we need to calculate transition dipole moment, and this should not be 0, this should not be 0 if your transition is allowed. And for this there are two criteria. One is molecule must have permanent dipole moment. If it does not have dipole moment, then this is going to be, your transition dipole moment is going to be 0. So, molecule must have permanent dipole moment, and then delta J must be plus minus 1, delta J must be plus minus 1. So, since your molecule must have permanent dipole moment, so transition are allowed in heterodiatomic diatomic molecule like CO, HF, NO, but it is not allowed in homo diatomic molecule, for example, S2Cl2 and N2. This is the rotational spectrum of CO, and you can see this is for J is equal to 3 to 9, and this is what has been obtained. And if you notice that in the, if you notice in the intensity, it is first going up and going down. Now, how to explain this phenomena in the rotational spectroscopy? So, as we discussed in previous lecture, that intensity is depending on the difference between population in the ground state and excited state. So, generally what we know is that number of species in jth level by number of species in 0th level can be calculated using Boltzmann distribution, which is basically exponential minus ER by kT. But here, since there is a your 2j plus 1 multiplicity, that will also come into picture, and your population also depends on multiplicity. So, basically in the rotational spectroscopy, both are going to influence your intensity. So, let us think about the different J levels, and so you see 0 to 14 J level, and this is your 2j plus 1. So, 2j plus 1 is calculated, and the second part is calculated exponential minus ER by kT. One thing you will notice is that this is increasing with the increase in J. 2j plus 1 is increasing with increase in J, whereas your exponential minus ER by kT is decreasing with the value of J is decreasing. So, one factor is increasing, another is decreasing. What happens that initially your 2j plus 1 factor is more predominant, and so what happens that intensity is going to increase, but on the later part your exponential minus ER by kT becomes predominant, and then your intensity starts decreasing. Till now we talked about rigid rotor, where we took R as constant, but in reality it does not happen as such. So, as the speed of rotation increases, nuclei tend to thrown outward by centrifugal forces. So, basically your bond is stretching, R increases and therefore B decreases. And for that, for example, if you take a diatomic linear molecule and if you take into account that R is not constant, you are going to get another term when we calculate your wave number. So, for rigid rotor we have Bjj plus 1, that is what is the wave number. What you get is another term which takes into account of distortion, So, minus d j square j plus 1 square, and we can again calculate nu bar. In this case it is simply by using your fj plus 1 minus fj plus 1. So, we are again looking for transition between jth level to j plus 1 level, since these are the allowed transition, and what you will get is 2b j plus 1 minus 4d j plus 1 cube. Okay, so, we will consider another different kind of molecule. Till now we are mostly confined ourselves to diatomic molecule. Now we will go to different kind of rotors. For example, if we have a prolate symmetric rotor, one example of that is CH3I. In that case, if we take Ci as the axis A, this is your B axis, this is your C axis, then your IC and IB will be equal. So, IC means your moment of inertia around axis C and axis B is going to be equal, while moment of inertia around A axis is going to be smaller, and your momentum will be given by K h bar. Hamiltonian of a prolate symmetrical rotor can be written in terms of its angular momentum operator. So, Hamiltonian is generally written as angular momentum square operator divided by 2IA plus angular momentum around B axis square of that, if you take operator, divided by 2IB plus LC square operator divided by 2IC. So, basically Hamiltonian operator is LA square operator divided by 2IA plus LB square operator by 2IB plus LC square operator by 2IC. But since IB and IC is equal, so you can write Hamiltonian operator as LA square operator divided by 2IA plus LB square operator plus LC square operator divided by 2IB, since IB and IC is equal. And now we also know that L square operator will be equal to L A square operator plus LB square operator plus LC square operator, and so LB square operator plus LC square operator will be equal to your L square operator minus LA square operator. And so, what we did is, in place of LB square operator plus LC square operator, we can put L square operator minus LA square operator. And then this can be written as, so if you take this term and bring it here, then what you will get is Hamiltonian for rotor is equal to L square operator divided by 2IB plus LA square operator divided by 2IA minus LB square operator divided by 2IB. So, from the last slide what we got is Hamiltonian operator for prolet rotor is angular momentum square operator divided by 2 IB plus LA square operator divided by 2 IA minus LA square operator divided by 2 IB. We know that L operator is equal to H cross J plus 1. So, L operator is equal to H cross square root of J plus 1. So, L square operator will be H bar square multiplied by J plus 1. So, that is what we are going to plug in this equation. So, when I put L square operator is equal to H cross square J plus 1, what I will get is this. Then for LA square, LA operator, that is equal to K H bar. So, for LA square operator, just plug in here, and what you are going to get is K square H bar square will be common, and what is left is 1 by 2 IA minus 1 by 2 IB. When we divide energy by H, we will get frequency, and this is the equation for frequency for a prolet rotor. So, H by 8 pi square IB J plus 1 plus K square H divided by 4 pi square multiplied by 1 divided by 2 IA minus 1 divided by 2 IB. So, if I take H by 8 pi square IB as B, and this H by 8 pi square IA is equal to A, then what I will get is your F, which is a function of J and K, and this is now a frequency, is equal to B J plus 1 plus A minus B K square. B and A are in hertz. So, you can also get this equation when you divide ER by SC, and ER by SC is also written in the same way, B J plus 1 plus A minus B multiplied by K square. Only thing is that now in that case B and A will be in wave number unit, and what I mean by that is A will be equal to H by 8 pi square IAC, and B will be equal to H by 8 pi square IBC. So, this equation sometime you will find in wave number unit, and sometime you will find in frequency unit. Both are same. Only difference is when you are talking about frequency, then A and B are in frequency unit, whereas when this F is in wave number unit, then A and B are also in wave number unit. This is here A is given in hertz, B is in hertz, but if I divide by C, then I will get A in wave number unit and B in wave number unit. Similarly, for oblate symmetric rotor, we can calculate the energy term. In this oblate symmetric rotor, the one which is not equal has highest moment of inertia along the axis which is not equal is higher than the moment of inertia along the two axes which are equal. So, IC is greater than IB is equal to IA, and this is typically a case of benzene molecule. And for that we can again write this, and that can be calculated the way we calculated for prolet, that HR is equal to L square by 2 IB plus LA square by 2 IC minus LB square by 2 IB, and similar way we can calculate the wave number for this oblate kind of rotor. For prolate oblate kind of molecule, the selection rule is delta J is equal to plus minus 1 and delta K is equal to 0, and so you can calculate the frequency or wave number of allowed transition, and that is simply 2b J plus 1. For a spherical rotor, it is quite simple, since you have I A is equal to I B is equal to I C. So, although the spherical rotor has no dipole moment, rotation around any of C3 axis results in centrifugal distortion in which other 3 hydrogen bonds are thrown outward slightly from the axis. This converts molecule into a symmetric rotor. And lastly, you have molecules like formaldehyde, which are asymmetric rotor, where IA, IB, IC are not equal. IB is but it is very difficult to calculate energy in this case. Today we have seen the theory behind rotational spectroscopy, and I would like to acknowledge these 3 books which I consulted for making all the notes, and thank you for listening. Thank you for listening.